Okay, so this morning, I was presenting you the simplest approach, very simple approach to calculate this decay rate for hypernuclears. So this was the picture I show you, and just because actually some of you, one of you actually asked me about how this is decomposed in the formula. I present just briefly how this is written. So in the first line you have the expression for the decay rate, right? So it's basically you compute this hypernuclear transition amplitude. So this is the one I was talking about this morning. This is a hypernuclear transition, this line here. And then you have, right. So this line here, and then this is the one that enters in the expression of the decay rate, right? And you basically compute the transition amplitude, square it, average over initial states, that will be this factor here, together with a sum over the spin projection of the initial hypernucleus, and then you have to sum over possible values of the quantum numbers of the particles in the final state. That means summing over the quantum numbers of the residual nucleus and summing over the quantum numbers of the two outgoing nucleons. So those things are, I'm going to put it in a file so you can have it, you can access to it, okay? And well, this is the composition I was talking about, the weak coupling scheme for the lambda, also how we extract one nucleon from the core, decoupling the nucleon from the residual nucleus. Okay, and once we have all these things decoupled, these particles decoupled, we can plug it in, and this is the more or less unfriendly equation that you get for the decay rate, right? These are just coupling and decoupling algebra, right? For isospin, from a spin, whatever, and this is the piece where the two-body matrix elements enter, right? And this is where the potential will enter, okay? The diagram corresponding to the potential. Okay, so this is just something that I wanted to show you, and then let's go to the point where we stopped this morning. So we stopped just commenting on those observables, and I say, okay, so let's now look which is the potential actually that the pion beam. Have no idea how they produce this pion beam. Do you mean that the one that I don't know? I have no idea. Actually, I really don't know the details of what is the source of these pions and I don't know either the source of the kaons, probably from some, I don't know, disintegration or whatever. And you know that, the production reaction for those things, I have no idea. There are many, many ways to get pions, so I don't know the specific one for this reaction. You have reactions where you produce these pions in the final state, and because they are charged, you can, if you do, for instance, proton-proton, proton-proton, going to proton-neutron, pi plus, I don't know, or maybe disintegration, actually, some disintegration process. I have no idea which is one, the specific channel for this one. But yeah, this is not something which is really complicated. And well, so in order to get the one meson exchange potential, right? So the easiest way is to start from the pion potential for the pion exchange. Okay, you have the lambda, right? Decay into a nucleon, and this will be the decay, the free decay of the lambda. Okay, the lambda in the free space. We know that this is the mesonic decay. So it's natural to think that the interaction of the lambda with another nucleon going to two nucleons will occur in the same way. So the pion which is emitted by the lambda at this vertex is absorbed by a nucleon in the medium, right? And then you close the diagram in that way, right? So this will be the first piece, okay? The first point, the starting point for the calculation of these diagrams. So this is the one diagram I depicted here. And what are the important point is to know what are the Hamiltonians or the vertices that we put in this diagram, this Feynman diagram. So basically, the parametrization that we use, I don't know why this is being shown in this funny way. So the parametrization we use for the weak vertex is the one I put it in the slide. So it basically has two pieces. It's a pseudo-scalar coupling at this vertex, right, of the form A plus B gamma 5 is of the pseudo-scalar type and has two constants, A and B. These two constants actually are fit to reproduce the decay rate of the lambda in free space, the two amplitudes, the parity violating and the parity conserving amplitudes of the decay. And so we take the same constants when evaluating the non-mesonic decay rate. So use the same constants that we have for the free decay of the lambda and use the same in order to parameterize the weak vertex in the non-mesonic decay, in this two-body interaction. And you see that the lambda has a quantity accompanying the field. Who knows what is this? This is called the isospurion, okay? This isospurion is a way to incorporate the delta isospin one-half rule in the mechanism. So we know that the lambda has isospin 0 and that the weak vertex violates isospin, right? So, and we have seen this morning that chances are that this violation of isospin is in 1/2, not in 3/2. So in order to apply all the known formalism related to isospin to these diagrams, in the same way we do for the strong interaction, what we do is to convert the lambda, to couple the lambda to an isospurion, okay, in such a way that you get a particle which has 0 charge, as the lambda is, but now has some isospin. So the delta isospin 1/2 takes place in the lambda line, in the baryon line. So you go from a state which has isospin 0 to a state which has isospin 1/2 and x is minus 1/2. It's like a neutron, right? From the point of view of isospin, it will behave like a neutron, okay? And then you can apply the isospin formalism as you do in nucleon-nucleon interaction for this reaction. And this is why here you see that you have tau here, operator, accompanying the pion field, okay? Once the lambda behaves like a neutron, okay? So instead of having the delta isospin happen in this vertex, you have moved it in here, okay? Regarding isospin. And, well, this parametrization is a little different from the one you have for the strong vertex, okay? What is the you know that you can use a pseudo-scalar or a pseudo-vector coupling or derivative coupling at the strong vertex, and when you use fields of positive energy, the result is exactly the same. You can check that. You can evaluate the vertex, this vertex here, the strong vertex between nucleons, using a pseudo-scalar form of this type, or a derivative coupling, which will be more suitable when one tries to describe chiral interactions, which are built among powers derivatives. So if you use a pseudo-scalar coupling or a derivative coupling, and you evaluate transition matrix elements between fields of positive energy, which are the ones we are using, the result is exactly the same. Actually, you can do it as an exercise, okay? It could be a typical exercise. I will put it in the sheet, okay? Formalize the exercise, the sheet of paper. And so now we have the two vertices, okay? this parameterization for this is standard parameterization for the weak one, and we have the pseudo-scalar coupling in the other side, okay? And then you need the meson propagator. The meson propagator that connects the two vertices in this diagram. Actually, when you write down when you want to obtain the potential, you have to start for the expression of the Feynman amplitude corresponding to any diagram that has this shape. Huh? The Feynman, just to make things clear, so you have here the position is x. Sorry. Can you see from the back? Yeah, the letter. Okay. This is x. This is y. This is the pion propagator. Okay. This point is y. I'm leaving factors here, I'm sorry, but I'm just interested in the form of the operators, and then I'm leaving factors. So just in order to write the correct expression, you have to look at the Hamiltonians I put there, okay? So expression for the Feynman amplitude, okay, is the one that you probably know. So here you have the fields representing the particles at the left, the vertex on the left. This is the Dirac operator for the vertex, so it's kind of coupling. Okay, we are putting. Then you have the pion propagator, the meson propagator, and then you have the particles on the other vertex connected through the appropriate Dirac operator, right? These fields here are the usual, have the usual expression, okay? And this is sorry, this is the spinor that we will actually work with, okay? When making the non-relativistic reduction, we will work with the spinor, conventional spinors, and we'll see what is the results of operating with these vertices, with this kind of couplings. And this will be this is the meson propagator. The meson propagator that you can write in terms of the distance, x minus y, or x minus y, x and y being the coordinates of the position of the vertices. And then you have here the 4 momentum square, okay? Okay. Well, actually, here you have to add for the propagator 2 pi over 3, right? Something like that. So this is the starting point. And then we start from this expression. One has to perform, from here, we perform an integration over time and energy variables. We can we can make a transformation to relative and center of mass coordinates in space, huh? Moreover, one can make an integration over the center of mass variables, huh? And at the end, you have an expression that you reduce non-relativistically. That means that all the factors that that appear in this expression with depends of Q0, you can make it to 0. So you basically make the limit Q0 equal to 0 and take the non-relativistic expression for these fields here. And at the end, And at the end, the expression that you get is you have made the transformation to relative and center of mass coordinates. So you can check all these expressions by making explicitly the transformation I was telling you times the integral over Q Here I have used this expression for the fields in order to get these exponentials. So you can just work these expressions and get to the one I'm writing down now. This is the standard way to obtain the potential okay. So this is basically this part here. If you look at this second part here, the second line, this is basically the Fourier transform of the potential in momentum space. Okay, so this part here is what at the end will give you. Okay, this can be. Do you see that? Okay, of the potential in momentum space. Okay, which is basically once you make the reduction. Okay, the non-relativistic reduction. So this exponential here factorizes, and then whatever you get left is you can identify with the potential. And as I said, you have to take the limit Q0 equal to 0 and then take the non-relativistic expression for the vertices, for the wave function, for the spinor, for the fields that appear in the expression. So the point will be, at the end, the calculation you have to do is to evaluate things like, so if you have the spinor, one spinor of momentum k, let's say, you can write this way here, okay? Oops, 1 sigma q over a plus m for one particle of mass m and energy E. What you do with this expression here is to basically take energy is very small, right, compared to the mass. So you can basically, momentum is small compared to the mass, so the energy is basically the mass. This factor goes to 1, and here you have 1 and sigma k over 2m. So this basically, you can take things like, in order to make the calculation much more easy to handle, right? And then you have to evaluate contractions. For instance, you see in the left vertex you have a constant A plus B gamma 5, and on the right-hand side you have a gamma 5, another constant gamma 5. So you basically have here two types of contractions. The one that takes you the unit in this left-hand side with the gamma 5 on the other side, and the other that gives you takes the gamma 5 on the left and the gamma 5 on the right, right? And this is a simple calculation. You basically take, imagine if, for instance, have a nucleon, okay? The spinor corresponding to a nucleon with momentum let me see, 3, okay? And I'm evaluating the left vertex, okay? The unit operator, and then you have a nucleon, and then you have the lambda with momentum p1, and then you have the propagator, and then you have on the right the other ones. So the only thing you have to do is take those spinors, okay, and make the products, okay? So you have 1 minus sigma by 3, 2mn, and then you have the unit, the identity here, and then you have for the lambda, you have 1 sigma. So this is sigma 1 because it's located on the vertex on the left, p1 over 2m lambda, okay? And this is a simple operation. That gives you 1 minus sigma 1 P3 sigma 1 P1 over 2m and 2m lambda. Okay? If instead of having the identity, which will be the one accompanying the constant term A, you have gamma 5, okay, you do the same operation but with the gamma 5. And the same on the other side. Okay? So when you do that with the gamma 5, okay, the gamma 5 is, you have to take the convention. You are used to work with the gamma matrices? Yeah, the gamma 5 is a 1. Otherwise, I mean, I can give you some, I will put some reference for the convention for the gamma matrices, because it depending on the convention you use, sometimes the results are a little bit different, okay? So, for the gamma 5, this is the typical one, which we have here. You operate in the same way, and the term you get is minus sigma 1 is sigma 1, sorry, over 2 sigma 1 P1 over 2 m lambda minus sigma 1 P3 over 2m. Okay? And then in order to make calculations much more easy and express this vertex as a function of the momentum transfer in the reaction, so in order to express the potential as a function of the momentum that carries the kaon, that means on the difference between P3 and P1, okay? What we do is to take average masses at the vertex. So we take, in this expression here, instead of having this term divided by m lambda and this term divided by m, with m is the mass of the nucleon, we take the average mass of the lambda and the nucleon and use the same mass. So we can actually factorize, okay, this term, working with we can factorize sigma 1 over 2 m average that multiplies P1 minus P3, right? Which will be the momentum transfer in the reaction. Q, okay? And then you have something here that depends on this momentum carried by the pion. Yeah? Okay, you have to do the same on the right-hand side, okay? And then you get a potential which depends on the momentum transfer, the momentum carried by the pion. What is the expression of this potential? Yes. This one? This is a constant multiplying the identity. No, pseudoscalar, you are absolutely right. Pseudoscalar is this coupling here, right? So this, we call it pseudoscalar parametrization because basically has a part which depends on gamma 5. But it also has a part which depends, which goes like an scalar, as you say, a unit. The point is that when you contract this vertex with this one, okay, the result is identity here, gamma 5 here, so you get as a whole, you get a gamma 5 contribution, which will violate parity in the process. While on the other hand, when you contract this one, this gamma 5 with with the gamma 5 that you have in this vertex here, you get something that conserves parity. In the same way you have for the nucleon-nucleon interaction, that you have gamma 5 here and gamma 5 here. This will come later. Okay, sigma mesons will come later because they don't appear in the ground state of mesons, right? So usually if you work in your one meson exchange model, I will not think on adding a sigma because, well, there are issues like which mass I will put for the sigma and other things like that. But at the end, you will see that the sigma actually plays an important role in this kind of very good of problems. So, so the potential one gets. The isospin appears here and appears here. The isospin, yeah. Right, this is a down because you don't want to change the charge of the lambda. The lambda has no charge. So in terms of the weak transition, if you want to dress the lambda with some isospin, and you want to preserve the charge of the lambda, you better couple an isosporion with the component. Well, because actually then you will have a positive charge there, and the lambda will have, you will be transforming the particle. Can you speak a little? Isosporion? No, it's not a multiplication. It's a couple. It's a way to represent the variation of isospin on the lambda field. So it's a coupling. It's a coupling. It's the same. It's this thing. So you, from the point of view, so this field has this form as a field, but also has some isospin, right? Also has an isospin. The wave function has an isospin. When you want to work the isospin in your process, has an isospin. What is the value of the isospin for this field? 0, right? Because the lambda has isospin 0. It's like if you here you will have a label saying the isospin of the field also. So it's a multiplicative factor if you want for each particle. Right? Yeah? The isospin. So, the way to incorporate this delta isospin 1/2 rule is to dress this particle which has isospin 0 with this isosporion, which will not change the charge, but will dress isospin with your particle in such a way that at the end, just forget about the momentum space part of this wave of this field, and concentrate on the isospin part. So you have a 0 isospin wave function coupled to a neutron-like isospin wave function. At the end, you have like a neutron-like particle in such a way that at the end, your problem from the isospin point of view only is like a neutron connected to a nucleon through the emission of a pion. And you can treat the interaction from the isospin point of view as you treat the nucleon-nucleon interaction. It's just a factor. It's just a Clash-Gordon, which is very simple. 0, 0, 0, 0 coupled to 1/2 minus 1/2 to give you 1/2 minus 1/2. Yeah, maybe I should have said that from the very beginning, right? So this is just taking the isospin of the lambda, okay, uncoupled to an isosporion, which is 1/2 minus 1/2 from the isospin point of view, right? You have to think that the weak interaction, the operator, okay, that makes the weak interaction carries this 1/2 isospin units in your vertex. So you have to put this isospin 1/2 operator in your vertex somehow, in some place, right? And the way to do it is to take the lambda. The easiest way to do it is take the lambda, dress it with, make the weak transition here, so you create a fake particle if you want, because it doesn't exist. A lambda with isospin 1/2 and projection -1/2 doesn't exist, but is the result of the weak operator acting in the isospin space on the lambda particle. More or less, it's a kind of, I know, uncomfortable, if you want, no, way to do things, but it works, and it's very easy to handle this kind of problems in a very easy way. So, well, once you work all these things, the potential you get, you can make the exercise. It's not complicated. It's basically calculate all these terms, right? The potential you get has 3 parts for pion exchange. I have to say, what is this sigma 1, 2? This is the tensor operator. Maybe not all of you are familiarized with the tensor operator, but when you make these calculations here, you get factors like sigma q, okay? If you do that, actually the exercise I was thinking on asking you was to evaluate the transition potential for the row exchange. I give you the Hamiltonian for the row exchange for each vertex, and then you derive in the same way. Okay, make the non-relativistic reduction, etc. And so you get terms that go like this. Okay? When you work the pion exchange. Well, all these terms here, you can actually, this is an operator that goes like q squared. And if you can see that if you take this operator and subtract this quantity, and I subtract this quantity, so you basically don't modify the expression, but you add and subtract this quantity here. Here is what is called the tensor operator. It's really tensor. That means that it will carry 2 units of momentum, of angular momentum, to your problem, to initial system, initial partial wave. So that means that your potential at the end will contain 3 different pieces from the point of view of how they behave in a spin space and in momentum space regarding the angular momentum. A part which is purely central, okay, that goes like q squared, but depends on sigma 1, sigma 2, this scalar product of the Pauli matrices. So it's a central spin-dependent operator. When you work out the row exchange, you will see that you will get, apart from this term here, a term which does not have a dependence on q squared. So a term which is purely sigma 1, which is purely q squared, sorry, which doesn't have this sigma 1, sigma 2. Okay, so you will get this piece here and another piece without this term here that goes like q squared in addition to this one. When you work out the row exchange, okay, that it will be an exercise. Then you have a tensor operator here, who gives you 2 units of angular momentum. And then you have a piece here that goes like q, sigma q. And this will be parity violating. Okay? So you have 2 pieces that conserve parity, goes like q squared. And a piece that goes like q and doesn't conserve parity. And if you think on the lambda in your hypernucleus, I told you that you can put the lambda in a shell model picture of your nucleus in the lowest energy level. So in this level here, okay, you put your lambda here. Your nucleon can be indifferent, right? Your nucleons, the nucleus to which the lambda interacts, etc., can be in any of these levels. And then you can have the in a spectroscopic notation, the coupled lambda n system can have indifferent values of L depending on where the nucleon is located, in which shell the nucleon is located, right? Let's take the simpler case in which you have a very light nucleus, where the nucleons and the lambda sit all of them in the 1s1/2 shell. Okay, so you have imagine you have 2 protons, 2 neutrons, and a lambda. So you have this system here, where you have 2 protons, 2 neutrons, and a lambda, all of them in the 1s1/2 shell, just to illustrate the simplest case. Okay, that means that the lambda n pair, the initial lambda n pair, will have relative angular momentum L equals 0, right? So the state will be an S state. Okay, because the lambda and the nucleon both have a spin 1/2, the coupled spin can be 0 or 1, and you can have a singlet state or a triplet state, right? Because the spin, okay, of the lambda is equal to the spin of the nucleon equal 1/2, right? So you can couple these two to 1 or 0. That means that you can have an S state in spectroscopic notation, singlet or triplet for the initial state, okay? And what will be the value of J? In this case will be 0, and in this case will be 1, okay? The result of coupling L and S. So imagine then that you are working with a very light hypernucleus, so that the lambda n initial state is in one of those partial waves. That means that each of these operators will take your system to a nuclear state which will be described by a different partial wave. The one that I think that Abraham Gal showed you some work with from Dalits. You were not here last week. You were here. Some parametrization, block and Dalits parametrization. Did you? No? You don't remember. Anyway, so it's very similar to this one here. So that means that the central part of the potential will not make any change in the spin or in the angular momentum. It carries, okay, 0 units of angular momentum, 0 units of spin. So it's a scalar, right, in a spin space. So it takes you the singlet state to the singlet state, or the triplet state to the triplet state. So these two transitions are driven by a central potential. Okay, the ones that change in parity, which will be this one here, goes from L equal to 0 to L equal to 1, okay, will be driven by this operator here, okay, which is parity violating, has 1 unit. It's an operator that goes like Q. Every time you have a momentum, you have to understand that you add 1 unit of angular momentum, because in one derivative in your problem, okay, the momentum. Vale? One derivative gives you 1 unit of momentum in the field, right? So that means 1 unit in angular momentum. So if you start from L equals 0, you go to L equal 1, okay? Through operators that depend on Q. While operators that depend on Q squared gives you 2 units of angular momentum. That means that you start from L equal to 0, you go to L equal to 2, right? And those are the transitions that you are allowed to have in this kind of with this kind of potentials. Okay? If you go to more massive nuclei, where you have nucleons also in a p shell, you can have relative momenta between the proton and between the nucleon and the lambda equal to 1, and the in the spectroscopic notation you can have p waves as a starting relative partial waves. The p waves through the central transition will go to p waves, through the parity violating transitions will go to s waves and to d waves. Okay, because you couple 1 to the initial angular momentum, which is L equal to 1. Okay, you go to from L equal to 1 to L equal to 0 and to L equal to 2, which violate parity because L has different parity. And the tensor transition will take you from L equal to 1 to L equal to 1 and L equal to 3. Okay, it has to preserve parity because the tensor is a parity conserving operator, right, with 2 units of. So this is the way we evaluate this kind of transitions happening through any meson exchange potential. Well, what happened? So if we look with more detail, this potential is dominated by the tensor part. Okay, this tensor operator dominates the pion exchange potential, and this has some consequences regarding some of the observables. One of the consequences is that if you remember this morning I was telling you about the ratio between neutron-neutron pairs and neutron-proton pairs in the detection as a final state. Okay, the experimentalists can detect in coincidence 2 neutrons or a neutron-proton pair, etc. Okay, this is one of the observables. If tensor transitions are dominating, okay, and you think you start from a partial wave in the lambda state with L equal to 0, 3s1, the tensor transition will take you to the 3.1 NN state. Okay, these are NN state. It will be the tensor transition. So imagine you have 2 neutrons. Okay, these 2 neutrons are 2 identical particles that the wave function has to be antisymmetric, right? And they have to satisfy that L plus S plus T, angular momentum, spin, and isospin of the pair has to be a knot quantity, right? Because of antisymmetry. If you are in a 3D state with L equal to 2 and S equal to 1, that implies that this 3D1 state can only happen for T equal to 0. So that means that neutron-neutron pairs are suppressed by this transition. So the dominant transition in the one-pion exchange mechanism, right, gives you nucleon-nucleon pairs which are basically of the type neutron-proton, right, which are T equal to 0, but no neutron-neutron. So that means that pion exchange gives you very small numbers for this quantity here. So if experimentally we detect very small numbers for these quantities, we're okay with that. But the point is that when we do the calculation, the number we get is of the order of 0.1 or something like that, while experimentalists get something much larger, 0.6, 0.7. So that means that we are missing something, so maybe pion exchange is not enough to describe the whole interaction. And okay, so we were very happy because we thought that with pion everything was, pion is simple and everything will be done already, but not. So we have to start adding all the mesons that somehow could interfere with the pion in such a way that will increase this quantity here, reducing this one here, so the decay rate, the total decay rate, which is pretty much reproduced by pion exchange, doesn't get too much alter, right? Too much change, so kind of balanced situation. So we start adding mesons to the mechanism and say, okay, how many mesons? So all the mesons, of course, right? So we have to start from all the pseudoscalar mesons, right? And continuing with the mesons up to 1 GeV of energy, right? But it's a pseudoscalar and vector mesons. The problem with this is that, well, all the mesons which are compatible, right? With charge, isospin, whatever. Transition. You can make the exercise and see that, well, if I have a pion that goes from the weak vertex to the strong vertex in this direction, if I have a pion, I can have also a rho, which has also isospin 1, okay? And can have the appropriate charge in such a way that if I go from a lambda to a neutron, I exchange a pi 0 or a rho 0. If I go from a lambda to a proton, I exchange a pi minus of a rho minus. So they are equivalent, more or less. One is pseudoscalar, the other one is a vector meson, but are both allowed. You can check that you can have also a eta and the vector partner of the eta, the omega, right? And if I place the weak vertex not on the on the lambda side of the diagram, but on the nucleon side of the diagram, I can also think of exchanging a kaon, okay? And so here you will have a nucleon, sorry, that enters this diagram here. The nucleon has isospin 1/2, and as isospin 1/2, and then you see that the coupling of the isospin of the nucleon with the isospin of the kaon. What is the isospin of the kaon? 1/2 gives you 0 or 1. So you see that the delta isospin 1/2 is happening in this part of the diagram, okay? So this will be the weak vertex, and this will be a strong vertex because you have isospin 0, isospin 1/2 which enters, and isospin 1/2 which leaves, okay? So actually you can have all of them. You can have all mesons belonging to the pseudoscalar octet or to the vector octet, okay? The thing is that you don't know what are the values, the exact values for the coupling constants of those baryons to these mesons, which are heavier than the pion. You don't have experimental measures for these quantities, and you have to rely to Lagrangians who are based in SU3 symmetry in order to relate the unknown coupling constants to the experimentally known coupling constants, which involve pions, okay? So, what are the diagrams? What are the Lagrangians that one uses? I'm not gonna go through the details of that, but for instance, the strong part, you can have, I will talk about effective theories to the weak sector, but this is something equivalent for the strong sector. So you can have a description of the interaction of baryons through an effective theory of QCD, so a theory which doesn't have the quarks and gluons as the degrees of freedom, but the appropriate degrees of freedom for nuclear physics, baryons, and mesons. And you can have, you can look at this. Are you familiar with this kind of Lagrangians? More or less, maybe some of you. Yeah. So, I mean, if you are interested, we can talk with more, giving you more details. So basically, gives you the kinetic term and the mass term for a vertex, which involves a baryon. Okay, of course. I mean, this mass term. So this is the baryon matrix, and this is the. I don't know if I have it. I didn't put the baryon matrix here. I'm so sorry. Do you know the baryon matrix? Do you have in mind the SU3 matrix for the baryons with the neutrons on? Yeah, I can put it in the slide in the file when that you will take home for the fireplace when you go home. So. When you do your course on hadronic spectroscopy, right? In your nuclear and particle course, undergraduate. So somehow you derive this matrix for the baryons, right? This is the charge, and so the third project of the isospin representation and the hypercharge on the vertical direction, right? So you put all the combinations that are combining the UD quark. Is the cascade, yeah. I don't know how to write that, so something like that. Yeah, I know, I'm sorry. Something like that. It's the cascade with two quarks, Z, 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 is the Z, 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 Z. Right, this is a strangeness -2, right? A strangeness -1, these ones here, a strangeness 0. So this is just the SU3 extension of the iso doublet for the nucleons, right? Well, and you have your representation for the mesons also, which is equivalent. Oops, this is a 6, okay? Pi minus, chi minus, k minus. Instead of a lambda, you have a eta. Instead of a sigma, you have a pion. You have the triplet, okay? The triplet here, doublet in isospin. Chi minus, chi bar 0, -2 square root of 6 eta. Okay, so you basically see the equivalence, right? The iso triplet, pions, the sigmas, the iso singlet lambda, the iso singlet eta, etc. Okay, so this is equivalence. So this will be for the pseudoscalar mesons, and you have the same for the vector mesons. Okay, so those are the matrices that enter in these expressions here. Okay, so it's very easy actually to work with this Lagrangian to obtain the couplings of the baryons with some mesons through these Lagrangians, because it's just multiplying matrices. You just have to multiply matrices, don't forget about signs on anything, and that's it, and you get the couplings. Okay, and this is a covariant derivative. In order to account for gauge invariance, you have to implement it here, and you have here the U, which is the exponential of these meson matrix. Huh? You can expand this exponential and work with one meson field, right? Which is what you are interested, because you are interested in one baryon going to another baryon, emitting or absorbing one meson. That means that you have to expand up to one meson field. Okay? You don't want to, if you are interested in processes in which two mesons are emitted, you have to keep two mesons in this expansion, so phi square. But if you are only interested in one meson exchange, you only keep up to this order. Then you plug this information, this expression in here, and you can just find all the possible couplings between mesons and baryons. Baryons and mesons, okay? You are right. This is only for pseudoscalar. If you want to go through vector meson, there is another expression. Okay? So, excuse me? You have to use the appropriate coupling. That's right. Yeah, actually you make me think I can write down the exact expression of this vector meson. This is based on vector meson dominance, actually, in the Lagrangian. Okay, so the point of that, the point of writing these things here is that just to let you know that, well, we don't know the value of these constants, but there is a way to obtain these constants from the theoretical point of view. Okay, you can calculate them, and you have the Lagrangian expressed in terms of these two constants, D and F. Okay, these D and F constants are low energy constants that are fit to experimental data, which is basically data related to pion emission or absorption, right? So, okay, so basically all the coupling constants that involve mesons heavier than the pion are related to the ones corresponding to the pion exchange, which is experimentally known. Okay, and for the you know is this expression here. So this is all the combinations that you can have that preserve the symmetries of the problem. So you can rearrange all the terms through first transformations, and then at the end you get these combinations here. You cannot have more of that. It has to do with the symmetry that you have here, you have placed here due to the strong interaction, all the symmetries that all the combination that you can have on the strong sector. It's the weight of you. It's a kind of it's not easy to explain it in words, so you have to actually write down all the possible combination that you have. You have the commutator going like D and the anti-commutator going like F, and all of them give you contributions that preserve all the quantum numbers that you have to conserve at the vertices. No? Yeah. Okay. No, but not all the couplings will get contributions for all the terms. Not all the. You can actually see that vertices involving different mesons and different baryons can contain only one of those constants, or sometimes both of them. Okay, it depends on the meson. So this is why I say it depends on the particles that you have involved in the vertex. At the end, you have to satisfy some conservation of quantum numbers here, and depending on the specific quantum numbers of the particles, then you have one, another, or a combination of both. Actually, it's very easy to check this because you are familiar with Mathematica, I guess, or with something similar to Mathematica, some software where you can make symbolic mathematics. Yeah. So you just plug this thing into Mathematica, not this one, of course, right? But the one that you are interested in, which is the coupling of the baryons to the mesons. You can code this thing in Mathematica. You can code these matrices. You can code these terms here, and get all the couplings for once. Okay, and you see which ones depend only on D, which ones depend only on F, depend on the combination. For the weak vertex, we have something which is more or less similar, with the extra consideration that you have to include a piece which takes into account this strange changing, okay, this variation of strangeness. Okay, this is the H matrix here. So this matrix here allows you to go through transitions that are delta S equal to 1, okay, which is what you have in the weak vertex. And this is a potential, a Lagrangian, that is derived in the framework of heavy baryon chiral perturbation theory, which has been worked for many years ago by Jenkins and Manohar, and has been applied in many weak processes. Again, you have constants that are fit to experimental data. Well, with all this in mind, working all these contributions to the one-meson exchange potential, one gets to a general potential that has this aspect here, which is organized in a central spin-independent piece, a central spin-dependent piece, sigma sigma, a tensor piece, and a parity-violating piece, which has two different contributions. If you work whatever I did before for pseudo-scalar mesons, you get a contribution like this. If you work the same thing for vector mesons, you get this contribution here. Okay? So the aspect the parity-violating contribution has for pseudo-scalar or vector mesons is a little bit different, but at the end the same consequences on the partial waves of the final state. Well, these are functions that depend on R and that multiply and that contain the R dependence of the potential. So this is just the final result. And this is what you will plug here in order to compute the rest of observables. Well, it's late. I will not start with effective theory because it's too much, I think. I will do it tomorrow. I mean, I wanted to talk you a little bit about lattice QCD, but if I don't have time, it's okay. Because lattice QCD is too complicated to just do that, blah, 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 you know? Maybe I will show some slides, some transparencies tomorrow, but that's it. But I'm just going to finish with the one-meson exchange model. Okay? So, you already told me this morning that Alfredo Poves was giving you some insight on what was the T-matrix equation, the Riemann-Schwinger equation, in order to account for the strong correlations between the nucleons. Is that right? Ah, no. Ah, I'm sorry. I understood that. Okay. Oh, yeah. Alfredo was here this week only. Okay. So you already, okay. You already hear about that. So just to tell you. So in order to account for the interaction, the strong interaction, because one thing is the weak transition, another thing is that the whole process, the nucleons feel also the strong interaction, the baryons among them. So you solve T-matrix equation, Riemann-Schwinger equations, with the input of successful one-meson exchange models for the strong sector. Okay. For the initial state, because the particles are bound in the nucleus, you have, instead of a T-matrix equation, you have to solve a G-matrix equation, which is the only difference that you put in a Pauli blocking operator in the expression of the G-matrix. So if this is the expression for the T-matrix, the diagrammatic representation of the T-matrix. So it's just summing all the ladder contributions. The G-matrix has the same kind of expression, but you insert in the numerator the Pauli blocking operator. That means that the nucleons that are propagating, okay, have to be able to access to levels which are not occupied, right? That's the only difference. And that it's much more complicated. Some numbers. So I'm showing you here the results of the theoretical predictions for one-meson exchange models, including this set of pseudoscalars and this set of vector mesons for the weak interaction for two nucleons, for a p-shell nucleus and a s-shell nucleus, and those are experimental data in different got in different labs at different years. for carbon and helium, okay? And you see that the predictions, in green, the ones for helium, in blue, the ones for carbon. For helium, well, they are not bad. Okay, you have to take into account that this is only one nucleon induced, right? So one has to add to the theoretical predictions the contributions of the two nucleon induced channel and of the mesonic channel that will shift these numbers a little bit to the right, okay? They add to this quantity, they will add to this quantity, so the agreement is not bad, it's quite good actually. And of course, as I told you, after considering also, just don't look at this with very detail to this transparent, after taking into account the propagation of the nucleus through the nuclear medium, okay, you also are able to agree in a quantity which is related to the ratio between neutron-neutron pairs and neutron-proton pairs, which is this ratio here, okay? So those are experimental numbers for carbon and helium, and these are the predictions of the one meson exchange model. So from this point of view of comparison of the experimental data with the model is doing well, okay? With the exception of the asymmetry that I have not shown you, because this is something I will discuss when I will talk on effective theory. But one could think, okay, I'm okay with that, so I don't need to go further, no? The motivation to do something alternative to this approach is to try to minimize the model dependencies of your calculation. So this is the basic motivation. Just go to an effective field theory description of the weak interaction in order to reduce the number of model ingredients in your calculation and do some more systematic calculation, okay? I'm sorry, I'm very slow, so tomorrow I will continue. Okay, sorry. Okay.